Okay, I want to have a look at Doppler here, but we already looked at Doppler, moving source, moving listener. If you haven't seen those little vids, check them out. This is relativistic Doppler. The whole point about Doppler, I think when we saw the moving source and we saw the moving receiver, we found that they were not relative. Okay, we couldn't just turn them around as if looking at it from the other one's point of view and call a moving source an actual moving receiver and call that the source just from a relative point of view. So that didn't work, and basically to do the whole Doppler thing we need to have something as a reference to measure our velocities from. And what Einstein showed, we haven't got into this in level 1, 2 or 3, but what Einstein showed was that you couldn't actually do this. There was no absolute frame of reference. Then the end effect of that is, and this is just what I want to show you on this little video here, is that you end up with a formula for the frequency, and you'll see that it's a little bit different, well, a little bit similar to the one we already had, so I'll call it f dash because that's what we're used to. You end up having this square root thing with c and plus v over c minus v, and this is all obviously multiplied by the original frequency. So that's how formula looks. Looks similar to the formula we had for the normal sound waves. What have we got here? Now, c is the speed of light, this one here, and v is the speed of the source if you're looking at it from that point of view. Remember, we're only going to get one equation here because it's all relative. So whether it's moving receiver, moving source, we can just use one equation. Now this v here, alright, is the v that we were talking about with the moving source. I've made it a negative. Negative just means it's moving towards the receiver. You might see the signs done around the opposite way. They've just turned it all round, but I call a negative moving towards the receiver. If you were to call a negative moving away from the receiver, then you'd have to change the signs. Likewise, the plus there is for a source moving towards the receiver. So it does what we'd pretty much expect. If we've got a negative on the bottom here and a positive on the top when it's moving towards the receiver, that's going to get smaller. This whole thing gets bigger, so the frequency gets higher. So it's pretty much what we'd expect. One equation to do both jobs. If you plug in your numbers, you'll get that. Now, the point is, you may get here these terms red shift and blue shift. They are related to the point that if we get a moving source that's coming towards us, the frequency is going to go up because of those, this one being subtracted, that one being added. The frequency is going to go up. That's equivalent to a blue shift. So when we look at the spectrum, we'll do more of that when we do the modern physics and the quantum, look at emission and absorption spectrums. We'll see what they mean by that. But basically, the frequencies of the lines in the spectrum are shifted, and they're shifted to the blue end because their frequencies are going up when we have the basically the source and the receiver moving towards each other. However, when they're moving away from each other, then this one on the bottom would get added and this one on the top would get subtracted, and the whole frequency would get decreased, and we call that a redshift. Smaller frequency, bigger wavelength, red, right? Higher frequency, shorter wavelength, blue. But this is the formula we actually use when we're doing light, because of that whole relativity thing. About all I wanted to say on it.